Hello, this is Jude Socrates and welcome to a portrait of linear algebra. Our video for today is about conditions for invertibility. So in the last couple of videos, we have learned a lot about bijective operators and about their corresponding invertible matrices. So in this video, we are going to learn a couple more things about these special operators and their matrices, and we will tie them all together into one really big theorem. So in this video, we will learn that the set of invertible n by n matrices is closed under matrix multiplication and also under scalar multiplication by a non-zero real number. We don't allow zero because if you multiply any matrix by zero, you get the zero matrix, and that's obviously not invertible. In fact, this is also true backwards. So we will learn that if the product of two n by n matrices is invertible, then both of those matrices had to be invertible. So this is actually going to be a homework problem, but we're going to mention it along the way. Oh, we just did. We will also learn that square matrices are invertible if and only if they can be factored into elementary matrices. We saw these matrices last time when we learned the algorithm to invert a matrix. We will show how to solve a system of linear equations which is square if the coefficient matrix happens to be invertible. And we will tie them all together in what we call the really big theorem on bijectivity and invertibility. As of now, it has 25 parts, and we will be adding 2 or 3 more conditions in the next few videos. Okay, so let's talk about closure. So far we have been referring to closure properties under vector addition or matrix addition, but this time it's about multiplication. So the theorem says that if A and B are invertible n by n matrices, then their product, A times B, is also invertible. And furthermore, AB quantity inverse, the inverse of the product, is the product B inverse times A inverse in that order. So we said that matrix multiplication is not necessarily commutative, so we have to make sure we write the product in the correct order. So analogously, if T1 and T2 are both invertible operators, they are both bijective, then the composition is also invertible. And furthermore, the inverse of the composition T2 composed T1 is the matrix of T1 inverse times the matrix of T2 inverse. Similarly, if K is a non-zero scalar, then K times A is also invertible, and the inverse of K times A is the reciprocal of K times A inverse. Okay, so let's prove the first equation, the first sentence. The others follow, okay, because if we regard matrix of T2 composed T1 by itself, we know from previous sections that that is the product matrix of T2 times the matrix of T1, again in that order. So if you invert that matrix product according to the first sentence, we should reverse the factors. So T1 inverse comes first, the matrix of T1 inverted, followed by the matrix of T2 inverted. Okay, so let's prove the first sentence. We're being asked to show that the product is invertible, A times B, and the inverse of that product is B inverse times A inverse. Well, this is where the 2-for-1 theorem becomes really useful. So it says that if you have a matrix and you think it's invertible, and you think, oh, I know who the inverse is, all you have to do is multiply the matrix to whatever you are guessing to be the inverse and show that it works, that when you multiply it together, you get identity. Okay, what property comes to mind? Okay, we're essentially multiplying four matrices together, but by the associative property, we can regroup the product so that we multiply the two inner matrices together first. So we have B times B inverse. Okay, and then on the right side of that product, we have A inverse. Okay, you can almost see it now. B times B inverse is just the identity. So that product, we have A times identity times A inverse. And again, we can choose to regroup this product into any grouping we want. So we can do A times IN times A inverse. And of course, A times IN is simply A. Any matrix multiplied by the identity is the same matrix. A times A inverse is your identity. So there you go. If you multiply AB by B inverse A inverse, after 4 or 5 steps, we get the identity. So therefore, B inverse A inverse has to be the inverse of AB by the 2-for-1 theorem. So the converse of this theorem is also true. If T1 and T2 are operators and the composition is invertible, it is both 1-to-1 and on-to, then both T2 and T1 are invertible. And analogously, if their corresponding matrices A and B are n by n matrices and the product A times B is invertible, then both A and B had to be invertible. So that formula, by the way, that we saw in the last theorem, that AB inverse is B inverse A inverse, that only works because we knew that A and B are both invertible. We don't know in this case that A and B are invertible. In fact, that's what we're trying to show. But that's what you're going to do in the homework. And in fact, you will find the formula for both A inverse and B inverse, and it will be in terms of the inverse of AB. The next property that we will show concerns elementary matrices. So remember that you obtain an elementary matrix from the identity matrix by performing a single row operation. You either scale one row, or you swap two rows, or you sum a row with a multiple of another row. This theorem says that an n by n matrix A is invertible if and only if it can be expressed as a product of elementary matrices. Now, in our last video, we showed that every elementary matrix is invertible, and in fact, the inverse is an elementary matrix as well, and it is of the same type. So the converse of this theorem is actually easy. You might say obvious. If a matrix is expressed as a product of elementary matrices, then we just said that each elementary matrix is invertible. But our last theorem said that if you multiply invertible matrices, you get another invertible matrix. So therefore, we get the converse. If you can express a matrix as a product of elementary matrices, then that product has to be invertible. The forward direction is not so obvious, but we have a formula for it. In the forward direction, if you have an invertible matrix A, we saw in our last video that you can find the inverse by augmenting A with the identity matrix on the right side. So you have this double wide n by 2n augmented matrix. Then we perform elementary row operations until we get the identity on the left of the augmented matrix, and on the right, miraculously, the inverse appears. So in the forwards direction, we can actually factor A using these elementary row operations. We can factor A as E1 inverse, E2 inverse, and so on, up to EK inverse, where E1 through EK are the elementary matrices corresponding to a sequence of elementary row operations that transforms A into the identity. So we will, of course, use the idea of the proof behind that theorem from the last video. So what did we do? We have A augmented by the identity, and then we perform an elementary row operation, so that corresponds to an elementary matrix E1. And we said that the effect of a row operation can be achieved by multiplying the matrix that we are operating on with the corresponding elementary matrix, and so on. We do another row operation and another until after k steps, we get the identity on the left and we get B on the right. But we said B, we had a name for it last time. We said that B is just A inverse. Okay, but what's important in this equation is the left side. Because we will have, if you remember this, we brought E1 inside and then E2 inside and so on. So you bring all of them inside, and so this long product times A is the identity, which is on the right side. We are now trying to solve for A, right? So isolate A on the left side. But that's where the invertibility of each of these elementary matrices is important. Let's get rid of EK first. So we can multiply both sides of this equation by EK inverse. Okay? So we have, again, the associative property. We can multiply EK inverse to EK first. That will give us the identity. And then we multiply that to the rest of this product. The identity goes away. And we just get EK minus 1 all the way down to E1. And then times A is EK inverse. And then, of course, you use exactly the same idea. So now you multiply both sides by EK minus 1 inverse. So what I want you to see is that when you perform that product, so let's do one more line, you are going to multiply both sides by EK minus 1 inverse. Okay? So this will go away. And actually, we will get EK minus 2 as the last factor on the left, okay? But we will invert EK minus 1 on both sides, multiply on the left of each side. So you will have EK minus 1 inverse to the left of EK minus 1, EK inverse rather. So that is why the last two factors in this formula are EK minus 1 inverse times EK inverse. And you keep going down, of course. So the last matrix that you will invert is E1, which is why the right side starts with E1 inverse. So let's apply that theorem to this example, which we saw in our last video. We augmented this matrix with identity on the right, and then we performed these 10 row operations. Okay, so if you recall, we were able to avoid fractions until 1, 2, 3, 4, 5, 6, the 7th step, all the way to the bottom row of that matrix. So what we're going to do now is we're going to apply our theorem. So you know what? Let's scroll up back here. And we said that the factorization that we want is this. Okay, so we want this factorization, E1 inverse, E2 inverse, and so on. So in this case, since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 operations, this means that our K is 10, and we have K minus 1 is 9. Okay, so what this means is we have to reverse each of these 10 row operations, and then we have to make the matrix corresponding to that reverse operation. that will be the corresponding elementary matrix. Okay, so I do apologize because we were so clever that our operations were mostly type 3. Okay, so those are all type 3s. These are type 3s. This is the only type 1. We never switched rows. Okay, so my bad, but we know what to do. Okay, we in fact just said in the last video that the inverse of a switch operation is the same operation, which makes sense. If you switch two things, how do you put it back in the correct order? You switch them again. Okay, so hopefully that won't be a problem. So now, what is the inverse of this operation? So, okay, what did we say? For a type 3 operation, instead of subtraction, we will have an addition. So what we will do is row 1 becomes row 1 plus row 2. Okay? And so on. What will be the inverse of this operation? Instead of subtracting twice row 1, we will be adding twice row 1. Okay? So we can do it for these operations. Just change the signs. Okay? So how about this one? This is a scale. What will be the inverse? So we said last time that the opposite of divide is to multiply. And of course, the inverse of multiply is to divide. Okay? So the inverse of this operation will be R3 becomes R3 times multiplied by negative 39. Okay? And if you don't look like that, maybe that doesn't look natural to you, you can also write it as row 3 becomes negative 39 times row 3. Okay, so the same for these operations. They will be just like these. Instead of minus 11, you'll get plus 11, and so on. Okay, so now let's assemble these 10 matrices. Okay, so I have made 10 copies of the identity matrix here. So yeah, it was too wide for just one line, so I might as well do it on 2 lines, and we'll just bring them together later on. So here are the first 5 identity matrices. So what are we going to do? For the first one, we need row 1 plus row 2. So row 1 is going to change. We will add row 2 to row 1. So that becomes a plus 1. Next, row 2 becomes row 2 plus twice row 1. So this is row 2. We add twice row 1. That becomes 2. Okay, now we have to reverse these operations and put down the effect on the next 3 matrices. So we have these 3. So instead of row 3 plus 4 row 1, we will need row 3 minus 4 row 1. So there's a 1 there. We need a minus 4 here. Then row 3 becomes row 3 plus twice row 2. So we subtract twice row 2. That's a minus 2. Okay, fifth one. Row 2 becomes row 2 plus 9 row 3. Here's row 2. We add 9 times row 3. So we have plus 9 over there. Okay, so now let's do the last 5. Okay, so here they are. 3, 4, 5. This one. So row 3 plus 2 row 2. So we will have plus 2 over here. The row 3 becomes negative 39 times row 3. So we multiply this by negative 39. Okay, not plus 39, minus 39. Okay, you keep the sign for a scale. Last 3. Row 1 becomes row 1 plus 11 row 3. So we need 11 over here. Row 2 plus 17 row 3. So this is plus 17. Last step, row 1 becomes row 1 minus 9 row 2. So we have a minus 9 over here. Okay, now it would have looked really spectacular if we just clicked on that one-liner and then see A come out, but we'll do it in 2 steps. So let's multiply these 5 matrices first, and boom, we get that answer. That's not A, okay? Now we multiply these 5 matrices together, and boom, that's not A either, but we're going to bring them together. So we will take our matrix here, and it's on the left, okay? And then we will take this matrix here, it goes on the right. Now we multiply those 2 together. So it's like we multiplied all 10 of them together at the same time. Less dramatically, though. Okay, do we get A? That looks like our A. So let's just compare. Let's copy that up here. And yep, it does look like our A. There you go. Why would I lie to you? All right, so in this theorem, we are actually going to see why the inverse of a matrix is useful, or at least what is one possible use for the inverse of a matrix. Well, it shouldn't be a surprise that you can use it to solve a system of linear equations. So, if A is an invertible n by n matrix, then the system AX equals B has exactly one solution for any n by 1 matrix B. So how do you solve for X? Well, we kind of did this a couple of minutes ago. Remember when we had EK on the left, and then we multiplied both sides by EK inverse? So it's exactly the same idea. You take this equation, multiply both sides on the left by A inverse. Okay, in other words, put the A inverse on the left of each side. So you get A inverse B. A inverse will cancel with the A to get the identity. Identity times X. Boom. More generally, this works if X is any n by m matrix. It doesn't need to have one column. Same idea, just multiply both sides of this equation to A inverse, putting A inverse on the left, and you get B is A inverse times C. Okay, so we're going to use the same example that we just looked at, same one from our last video, where we saw, of course, we were computing the inverse of that matrix. We are going to use the idea that we just saw to solve the system of equations. Now, of course, these numbers here are exactly the entries in our matrix that we just inverted. So we have 3 minus 8, 5, 3x minus 8y plus 5z equals something. So the theorem said, it doesn't matter what you put on the right side of this system, that system will be solvable. And we have a formula for the solutions. So just make sure, because after all, the first rule of math is make sure you copy the problem correctly. We have 2, 1 minus 6 here, 2x plus 1y minus 6z. Anything on the right side. Last equation, minus 4x. There's no y here, so there is no y there. Plus 7z equals anything you want. So we're going to solve this system. Okay, so the first step is to recognize that this system that we have can be written as a matrix product. So again, we have the coefficient matrix, which is exactly the same matrix we were playing with, but now we have the variables x, y, z. So that matrix product is essentially the left side of the system. On the right side, you have minus 4, 9, minus 3. So that is written as a column vector. So the theorem said, if you want x, y, z, then what you need is the inverse of the matrix, which is over here, and then you multiply it to the right side, which is this. Okay? So our solution xyz is just the product of those. So those are the answers. Let's copy that up here. So there you go. Now it looks nicer. So we get x has to be minus 347 over 39, y has to be minus 245 over 39, and z has to be minus 215 over 39. Kind of ugly, right? But that's expected because we do have the 39 denominators in our matrix inverse. Okay, so we have reached the end of chapter 3, and this is truly a grand finale. Since section 3.6, we have been looking at bijective operators and at their corresponding invertible matrices. So we are going to tie all the concepts that we have seen regarding bijective operators and invertible matrices into one big theorem, and we're going to see that the parts are tied together by some very important theorems that we have also seen. For example, the dimension theorem. Okay, the rank plus the nullity of a matrix is the number of columns. Same thing with an operator or any linear transformation. The rank of a transformation plus its nullity is the dimension of the domain of the transformation. But in this case, of course, since we have an operator, the dimension and the codomain are exactly the same space, and that dimension is n. Okay, so the really big theorem on invertibility and bijectivity says that the following 25 conditions on an operator, T from Rn to Rn, and its standard matrix, the matrix of T, we'll call it A, which is an n by n matrix, that these 25 conditions are all true for that matrix, for that operator, or they are all false. So in other words, each pair of these conditions is an if and only if statement. Okay, so for example, pick any two that you want. We can say that T is injective one-to-one if and only if the columns of the matrix of T span all of Rn. Okay, so that's one possible pair. So basically, as we read these statements, we are going to just think to ourselves, if T is a bijective operator, then its matrix A has to be an invertible matrix, and vice versa. Okay, so basically, each of the 25 parts are equivalent to every other of the 25 parts. Okay, so let's read them one at a time. So the first condition says, T is a bijective operator. In other words, that definition is T is both injective and surjective. One-to-one on two. Okay, so we have reminded you here what these words mean. Okay, condition 2, A is an invertible matrix. What was the definition? We said that a matrix is invertible if and only if its corresponding operator, where T of V is A times V, is a bijective operator. It's one-to-one and on-to. Oh, so 2 implies 1 and 1 implies 2. That's really the definition of an invertible matrix. We said that a matrix is invertible if and only if its REF is the identity. And why is that so? You want your operator to be both injective and surjective. So if you want it to be injective, sneak peek, we said that, and review, T is injective if and only if its kernel is only the zero vector, meaning there are no free variables in the REF. Okay, and if there are no free variables, the REF has to be the identity. Okay, if it's not the identity, you run out of leading ones, you have to have a free variable. Okay, we just proved that A is invertible if and only if it is the product of elementary matrices. Okay, so we said that an operator is one-to-one if and only if its kernel is only the zero vector. Okay, but wait a minute. Now it becomes a little murky because, wait a minute, we said you had to be both injective and surjective. So why is number 5 just saying, oh, T only has to be injective? I hope you remember, we also had a 2-for-1 theorem. So it said that T is injective if and only if T is also on 2, because of the dimension theorem. If T is injective, the nullity is 0, so the rank has to be n, which means that T is on 2. Aha! So, of course, this next condition is equivalent to the null space being only the 0 vector, because the only subspace of Rn that has dimension 0 is the 0 subspace. And of course, nullity means the dimension of the null space. So similarly, T is both injective and surjective if and only if T is only surjective. Because if it's surjective, then the rank is n, the nullity is 0, T is also 1-to-1, 2-for-1. What does surjective mean? The range of T has to be all of Rn, which means that the rank of T has to be n. Okay, so what are we seeing here? 5, 6, and 7 are all variations on the same theme. 8, 9, and 10 are also variations on the same theme. But wait, of course there's more. What is the meaning of the range? It is the span of the columns. So if the range is all of Rn, then the columns of A must span all of Rn. 12 is kind of cheap. The span of the columns is the column space, right? So 12 is really just another way to write 11. But it kind of looks nice because it talks about a subspace. So, speaking of subspace, we said that every subspace has a basis, okay? So if the column space is all of Rn, then the columns of A must form a basis for Rn. So remember, we also have a 2-for-1 theorem for a basis, okay? We said that if you know the dimension of a subspace, let's say it's K, and then you have a set of K vectors from that subspace, how do you know if these vectors form a basis for the subspace? So instead of having to check 2 conditions, you only have to check 1 condition. Either it is an independent set of vectors or it spans the subspace. And we said in practice, it's easier to check independence because all you have to do is look at an REF. Okay. So how many columns do you have? You have n columns. So if the column space is all of Rn, oh, wait a minute, that means that the columns must span Rn. Oh, we just said those mean the same thing. So by the 2-for-1 theorem, you have a basis for Rn, and therefore you also get the independent condition. And of course that works backwards. If you have n independent columns, do they form a basis for Rn? Yes, because Rn has dimension n, and you have the correct number of vectors. The number of columns is also n. So you can say the same thing for rows. The rows of A span all of Rn. The row space, which is the span of rows, is Rn. The rows of A form a basis for Rn. The rows of A are linearly independent. What's the connection between rows and columns? We also, of course, said that the dimension of the row space is exactly the same as the dimension of the column space. So, therefore, if the column space is Rn, then the row space also has to be Rn. Okay, so now let's talk about the inverse matrix. Okay, so recall that if you have an invertible matrix, the matrix B, which is the inverse of A, has to satisfy 2 equations. A times B has to be the identity, but also B times A has to be the identity. Oh, I hope you remember, we had a 2-for-1 theorem there. We said that if you have a candidate B for the inverse of a matrix, and you check that A times B is the identity, then you also get for free that B times A is also the identity. So 19 and 20 are exactly the 2-for-1 theorems. So we have a few more. So the last 5 conditions are basically about systems of equations. So number 21 is about a homogeneous system of equations. It has only the trivial solution. But wait a minute, where did we see this homogeneous system when we talked about the null space of the matrix? So we said a matrix or an operator is 1-to-1 if and only if its null space is only the 0 vector, which means that the solutions to the homogeneous system is only the trivial solution. X is all zeros. So therefore, 21 is the same condition equivalent to T being 1-to-1, which we know is equivalent to T being bijective. The last 4 conditions are in your homework, okay? But let's just look at them because they all involve, well, these 3 involve AX equals B, which is a system. But this involves the augmented matrix, A augmented with B. Of course, that also represents a system of equations. So number 22 says, for all B in Rn, the system AX equals B is always consistent. Why does that mean that your matrix A is invertible? That's your homework. 23 is slightly different. For all B in Rn, the system AX equals B has exactly one solution. Well, doesn't consistent mean exactly one solution? Oh, no. Consistent means at least one solution. 23 says exactly one solution. So if you just heard what I said, you know that either 22 implies 23 or 23 implies 22. Which is which? 24 is probably the most mysterious of these 3 conditions. There exists a B in Rn such that the system AX equals B has exactly one solution. Okay, so this is quite different. In 22 and 23, you can put any B that you want on the right side of these equations. Any B you want at all. 24, no. Someone makes a choice for you. Someone finds a B in Rn so that this system, AX equals B, has exactly one solution. Now that's enough to conclude that A has to be invertible. Think about that. Okay, so the last condition. For all B in Rn, the rank of A is exactly the same as the rank of the augmented matrix, A augmented by B. Okay, so what does rank mean? It's the number of leading ones in the REF. Okay, don't forget that part. I almost did. Look at the REF of A. You will have K leading ones. All right, we don't know yet that it will have N leading ones. It might have only K leading ones where K is less than or equal to N. But the rank of the augmented matrix, A augmented by B, is the same as the rank of A. For any B in Rn, no matter what B you put on the right side, if you find the REF of that augmented matrix, you will have the same number of leading ones as the REF of A. Why is that enough to conclude that A has to be invertible? So think about those 4 conditions. So a couple of years ago, I thought, you know what? I want to see all of the 25 parts in one big diagram. And it was really hard to kind of make them all fit nicely next to each other until I came up with this diagram. Okay, so I decided to put 1 and 2 in kind of the center. I guess that would be where your heart would be if this were a person. And so we have these two first conditions as basically definitions for what an invertible matrix is. So what do we have around it, right? So we have the kernel test over here, which is of course connected to the one-to-one property and to the nullity, okay? So we said that, oh, if you want bijective, it's enough to be only injective by the 2-for-1 theorem. And similarly, you only have to be surjective, okay? So T being on 2 is the same as having the rank of T is n. So full disclosure, I repeated number 10 kind of down here, okay? Because the rank has to do with the dimension of the column space and the dimension of the row space, okay? We just mentioned that they're exactly the same, okay? So if we just scroll here a little bit, you have all of the parts concerning the row space down here on the left, and all of the parts concerning the column space here on the right. Okay, so that takes care of the bottom of the diagram. Talk about gray area. These 4 gray boxes are your homework. Okay, parts 22, 23, 24, and 25. Okay, so looking back here, we have the existence of the inverse matrix on the sides over here. A is invertible if and only if the REF is the identity. And of course, that means that the rank is n. Full rank, it's as big as possible. And the REF is the identity if and only if A is the product of elementary matrices. So I believe that is all 25 parts in one picture. All right, so that is our video for today. This is Jude Socrates signing off. Thank you very much for watching. As usual, you will find me on Facebook, and you will find the 4th edition on Facebook and at kendallhunt.com. So until our next video, enjoy the rest of your day.